So, today we're going to be doing production Huff. So this is going to be looking at, kind of best practices, some good ideas of, things that you should be doing, shouldn't be doing. We'll take a look at the Huff style guide, and we'll also briefly take a look at some Huff that is in production today. So before anything else, before you write any code at all, we have specifications, right? So this guy Mohammed has kind of been a mentor to me more recently, but something that really stuck with me that he said is that two different engineers with the same specification should be able to produce functionally equivalent implementations without communicating, right? So that means if these guys don't talk to one another, they have no idea like what the other one's building. As long as they have that same spec, whatever they implement in whatever language, right, the same input should map to the same outputs, right? So we don't know what that thing do. So we need to know, what the specification should constrain, right? Is first your ABI, right? So that's your function selectors, your event signatures, things like that. You should also constrain the behavior of each valid function, right? So that's branches and their threshold, exceptional cases, event logs, things like that. And then finally, we have properties, which are like invariants and assumptions, right? So, with things like branches and thresholds, these are things like, what if you do, what do you do if like a balance is above a certain amount, or if this number is like greater than or less than that thing, right? Like, um, let's say like you want to make a transfer, right? Like what happens if your balance is, like what happens if your balance is like less than the amount, right? Like what exactly should happen? Obviously we know it's an exception, but that's something that should be constrained by the specification, right? And then in terms of things like invariants and assumptions, so your invariants are like these they're sort of like predicates, right? Like they're these expressions that should always evaluate the true, right? So like in the case of Uniswap, right, the x times y equals k, right? Like that's something that you can check, and if it evaluates defaults, then we know that the invariant is broken, right? And then assumptions are like not quite as serious as invariants. They're kind of more just like um, they're kind of just these assumptions that we make about general behavior that if violated it doesn't break anything. It's just something that would kind of, I guess, make their life easier, right? Like we assume that things are encoded the correct way, right? Like we just kind of like take that at face value, right? And if something breaks, right? But the idea is that like our specification should constrain that if something should break, it will break, right? So after specifications we have incremental implementation. So a while back there was this workshop on like refactoring and things like that by someone named Sandy Metz, and more or less what she said was your test should be written in such a way that any change that doesn't cause a test failure is a valid change, right? And so the idea behind this, right, is if you have a good enough test suite that fully constrains your specification, it checks invariants, all of that, then you know that if you make a change, right, whether it's optimization or code organization, you know that that change, if the tests all pass, is a valid change, right? So, first you got to crawl before you can walk. So crawling is you write the specification in a high-level language, right? We need a high-level reference implementation. And so with that, we need to write a full test suite for the high-level implementation. So that means concrete tests. These are tests with like constant, concrete values. We have stateless fuzzing, which is where you just throw a bunch of random values at it, um, and you evaluate, the output state of that, right? And then you have stateful fuzzing, right, which is also known as invariant testing. And so this is a bit broader and this is a bit more complicated, right? But it still is focused on the same principle of we're throwing a lot of random values at things, over time and expecting that the invariants that we declared in the specification actually do hold, right? Now, once you've done all this, you actually want to start optimizing this high-level reference implementation with inline assembly as much as possible, right? And the reason for this, like the reason that you want to start, optimizing with inline assembly is if you're going to be writing Huff, you're going to be interacting with opcodes pretty much directly, right? And so you want a bit of a clearer, like you want your abstraction to be a bit clearer, right? By writing in something in Solidity, for example, like you should see like what actual opcodes are you using, And then from that, you can build that, in Huff, and you can start building a good stack schedule and things like that, right? But the most important thing out of all of this is make sure all of your tests pass before the next step. So next you need to walk then run, right? So you want to implement the specification in Huff, right? You want to match the reference implementation's ABI, right? So you want to make sure that all the same function selectors map to the same places. You want to make sure the encoding is still the same, things like that, and you want to assert that all the tests still pass. And once you can run, then you can fly, right? So if everything else works, if your tests still pass on the Huff implementation, right? Like you've already kind of done this migration into Huff, and so you pretty much already have everything you need, right? But if you still need more gas optimization, one way is to write your own ABI encoding, right? So obviously to interface with this, you'll probably need some kind of encoder library, maybe some custom data types, right? But you should be able to get a ton of gas savings out of an ABI encoding because call data is actually surprisingly expensive. Next up, you can unroll loops with a known upper bound. So this is a bit of a weird optimization, but it is a macro and it can actually save you quite a bit of gas. The idea is just being that if you have a loop that is never going to iterate more than like 10 times, right, then you can basically just unroll that loop and just write that block 10 times, right? And there's other ways of like kind of using a stack-based system to avoid to avoid having to do this loop, right? Because looping has to do with a lot of like conditions and jumping and going back and forth, and it's just it gets a bit messy. So next up is optimizing the stack schedule. So I'm not going to go super deep into this one here, but this is actually a pretty powerful optimization here that there was this paper that came out not too long ago about like a tree-based intermediate representation, compiler tech, yada yada. But basically, what the idea was, right, is that you can create a graph of opcodes, and that graph it's structured in such a way that if you do a depth first traversal, it'll generate the optimal stack schedule, right? And so this is a bunch of like I don't know, really deep like research stuff as to like how this stuff works and why it works and all that. But I did notice that the way that I actually schedule the stack is a lot different after reading this thing. So I'll be sure to link that here in a little bit. But basically, the idea is that like you want to minimize obviously duplication, you want to minimize swapping, right? You want to set the stack up in such a way that you have to do the minimal operations, right? Um, you want to do the minimal like number of operations, right, to get whatever you need done to get done, right? And then last thing that I'll recommend is read compiler optimization rules, right? So pretty much every EVM compiler out there has a backend or an intermediate representation, and somewhere in there is an optimizer. Sometimes it's called simplification rules, right? But I highly recommend that you go and check these out and any compilers you're interested in. Because some of these are like really simple, it's like, oh, if a value's been pushed to the stack and immediately popped, then remove it, duh. But it also has other things like finding loop invariants. It has things like, detecting things that are functionally equivalent that we can just totally like, remove from the bytecode and get some pretty sweet optimizations out of. So highly recommend reading those simplification rules when you have some free time. So once you've done all that, you have everything put together, everything's good to go. Next up is documentation and periphery. Now, if you write hyper-optimized, obscure Huff code and you don't properly document it, when you go home, I'll be under your bed. This is me threatening you. Please, for the love of God, write documentation. So what does this look like? You want stack comments on every line with an opcode, right? And that's something that Shafu was showing us earlier with the stackgen, the code comment like generation, right? And that's a great start, right? But you also want to make sure that things are like named very well and that it's very intuitive to follow the state of the stack all throughout your program, right? Now, the next thing is you want to document every macro, every function, every constant, everything that exists in your file should have some kind of documentation, right? For macros and functions, you want to explain the high-level procedures. You want to declare your invariants. You want to declare your assumptions. You want to declare conditions that revert the transaction, like everything that could happen within your macro or function, you should document it there, right? Like just above it. Now, of course, no amount of documentation is too much documentation. Um, as long as you have like good docs on this stuff and make sure that it's very, very explicit, that's what's really important, right? Because there's going to be somebody that comes along that wants to read your code that maybe doesn't have the same context, or maybe they just, there's going to be somebody that's going to want more context, right? So always make sure you have as much context as possible. Now, in terms of readability, like I said, we'll go more into this in just a little bit, but some of the TLDR stuff, right, is you want to align the opcodes, so that's like alignment in terms of tabs, right? You want to avoid multiple opcodes per line. Now, there are exceptions to this, right? Things like the function selector dispatcher, that totally makes sense. It's a very, very common pattern. Like there's no reason to sit there and put that over multiple lines whenever you can just like group a couple of those opcodes together. But in general, you want to avoid multiple opcodes per line. Next up, you want to indent conditional blocks, right? So if something's conditional, just add an extra layer of indentation, and it kind of gives you this readability of like an if-else or like a loop, right? And then last thing here is follow consistent naming of constants and macros, right? So kind of a little bit of a pattern that I like to use here, right, is if something's a storage slot, we just suffix it with underscore slot. If it's a selector, we suffix it with cell. If it's a pointer, we suffix it with PTR. If we have some kind of macro that does sort of typecasting, maybe it does some kind of like constraint on bits, or it cleans, dirty bits, things like that. I like to say to data type, whatever that is that we're looking to create. And then any libraries that we're creating that are external to it, I like to prefix it with lib. It just keeps it pretty simple. It looks pretty clean. So like, lib, like lib error, lib transfer, things like that. And you can just import those straight into your project. Now, as for periphery, if the ABI is the same as Sol-C, there's not really much you have to do with this. Client libraries should be able to interface with it, off-chain with no problems. So that's REST libraries, TypeScript libraries, things like that. And then standard Sol-C interfaces can also be used to interface with it on-chain. Right, but if you don't have this, if you do have some kind of custom ABI encoding scheme, it's a good idea to write at least a minimal client library to interface with it off-chain. So that's either in Rust or TypeScript or Python, whatever your poison. And then it's a good idea to also have a minimal library or some kind of like custom data type to interface with it on-chain, right? Something that you can pretty simply interact with, and of course you're going to need this for your tests anyway, but it's also a pretty good idea, for anybody else that wants to come along and hit the contract that you've built. So once you've done all of that, you've built everything out, you've got your specification, all of your test pass, periphery and documentation, everything is good to go. Next up, you have deployment. And that's it. You got to fuck around and find out. This is, like I said, a pretty high level guide overall. But I think this should be, more than enough to like get the ball rolling on, like getting something to a place that is production ready, that can be reviewed by an auditor. Even if they do have to be a little specialized, the idea is still that this is still very much like plausible for somebody to actually like read and reason about, right? Because sometimes, especially like, I mean, even myself, some of the early Huff projects, right, like they were very, very hard to read, very hard to reason about. The tests weren't all that great, right? So just making sure you have all those bases covered there. Next up, we'll jump very briefly into the Huff style guide. Share the compiler optimization. Yes, I'll share that in just a moment. I'll send over some links for the Solidity one, and I'm not sure where the one for Viper is. I haven't looked into that one, but I'll definitely send over the Solidity one in a bit. But next up, we have the Huff style guide, right? So this is a mostly reasonable approach to Huff styling. This is kind of a nod to Airbnb's like JSX and like JavaScript style guide. Just something that in general just kind of gives you guidelines as to like what good styling looks like for this kind of stuff, right? And I think this is also like a good like foundation for creating something like Huff FMT, right? Something that can like format this code automatically. So basic rules, generally you want to go with one opcode per line, right? Now the exceptions here are, if the first opcode of the line is followed by dupe instruction. So if you just have to dupe something like 3 or 4 times, right, that makes sense to put them all in the same line. There are some cases where, if you have like a pointer and then a load instruction right after that, that kind of makes sense to have on the same line. And then, of course, standard function selector dispatcher. This is what I was talking about earlier. This is a really, really common pattern that you'll see, right? The call data load, bit shift, and then just sit there and dupe and do the equality checks, right? Like that totally makes sense. to keep those kind of grouped up together. And then if you have a return or revert with no return data, that kind of makes sense as well, right? So something that, here we go. Something that's basically just like, put 2 zeros on the stack and just halt the execution. This kind of makes, this makes sense to like put this all in one line, right? Next rule, like I mentioned earlier, prefix libraries with lib. That's just a pretty simple and straightforward way to go about this stuff. In terms of items that are in the files, generally they're ordered roughly along the lines of your include directives, right? So these are like your imports. Then we have ABI definitions. So anything that's related to ABI, we want that to come next. We want constants to come after that. Next up, we have the constructor. So this is your initialization code, what gets run, when you deploy the contract. Obviously main, which is your entry point. And then anything after that is going to be macro and function definition, right? And this is just kind of a way to make sure that everything's separated out, the right way and in an intuitive way. In terms of macros and functions, obviously you always want to make sure that the input and output stack states are properly constrained. Make sure that these things line up properly. Now for macros, obviously this isn't checked, so you kind of can get away with it, but you do want to make sure for readability's sake that is correct. Now in terms of functions, that's like define fn. It has the same syntax as a macro otherwise. This actually jumps to another point in the code, executes the block, and then jumps back. And so that's actually a problem if the stack state is not correct, because it actually pushes the jump desk to get back, like just before the function starts, right? So if your stack state's incorrect, it's going to consume things the wrong way, and you're going to end up with these like really weird edge cases where stuff just like doesn't work correctly. So always want to make sure that you constrain these, even if the compiler doesn't force you to just yet. Next up is template args. Generally, you want them to go on a single line, but of course, if it's gonna be some crazy long line, it's totally okay to put these things on their own line like that, right? In terms of naming, like I mentioned earlier, slot, cell, PTR, the typecasting, right? Things like that. Of course, in general, you want macros and functions. You want these to be, well, okay, so whenever it's related directly to like an ABI thing, you just want it to be in like this screaming snake case, right? So like the get by index external function, like this sort of like ABI thing. If you have a macro that directly maps to that, it's a good idea to just give it the same name like that. Let's see, ABI things. So yeah, of course, in general, like it's a good idea to at least start with like a Solidity style ABI, and generally like you're going to get a lot of optimizations out of just switching over to Huff. But if you absolutely need to squeeze every single byte out, of course you can write your own call data encoding scheme. Now, I like to keep this in libabi. It's just like a pretty standard place to keep it. And then next thing here, like sort of a style guideline for defining this ABI spec, it's a really good idea to have this sort of dev doc style thing that indicates like what the layout is, right? So like this get function, for example, it's just a very simple, like no arguments. It's just got a single item here, right? But in cases where it's multiple, maybe you want to specify like its selector concatenated with a number, and you say the sizes of everything, stuff like that, right? Just as a way to like very explicitly declare like what is every byte, how many bytes does each thing take, how are these things all laid out, et cetera, et cetera. In terms of alignment, like I mentioned earlier, just make sure everything follows the same spacing. If it's conditional, just give it a little indent. It looks nice and clean like that. Nesting indents are also okay. And you kind of just follow that process recursively. Next is stack comments. So obviously we know about the basic stuff of stack comments. Another general guideline that I like to follow here is if it takes some non-zero amount of stack items, I like just putting this extra piece here that indicates like what it looks like in the beginning, and that way it's a bit more intuitive of like how to interact with it throughout your macro. Of course, we want everything to be aligned the same way. If you can align everything in the file together, that would be great. But obviously, sometimes that kind of gets out of hand. So even just making sure they're all lined up in the same macro is a really good practice. I've also got some general guidelines on how to name things with, name things in the stack comments. So like suffix with dest means that it's like a jump destination. Mem pointer, CD pointer indicates like where it's pointing to. Anything that's like a length or a size, just suffix it with len. And sometimes there's not really a good name for whatever you're using, so if all else fails, you could just say 0 or 1, right? In general, you want to avoid that, but it is something that you absolutely could do. And then last thing here is dev docs. So obviously at the moment, Huff doesn't have any kind of like dev doc generation or anything like that, but this is something that we'd love to add, eventually. So in general, I'm kind of following roughly the same patterns as Rust, using GitHub, flavored Markdown, and using / exclamation point at the top level, like file, right? At the start of the file, and then triple slashes above each item there, right? So what that might look like is, to document the compute hash, we have this bit of dev doc here, right? And like I mentioned earlier, you have these like high level like directives, right? Like how things work. And then you want to add things like, revert cases and things like that as well, right? So that's pretty much it for the style guide. And then very briefly, as we wrap this up, I'll go ahead and show you real quick what something like this looks like in production, right? So we managed to actually get, into the Artemis bot, Paradigm's MEV bot. We managed to get an arbitrage strategy contract built into this, right? So just diving into this really quick, this is kind of what the specification looks like for the Huff contract, right? So we take all the data structures that we expect to see, within the context of this stuff. We just define all of that here. We have the call data layout, right? So dot just means concatenation in this case. And then you can go through and see like what the size of everything is, right? And just like where everything sits in the call data, right? A little bit more about like just general functions that we have in this. The strategy contract is ownable, of course, so we have a little bit for that. And so here's like the mid to high level implementation, right? It's still written in Solidity at this point, even though most of it is in assembly, right? So you have this execute arb function. This is something that they had on their original version anyway, but you'll see pretty much everything in here is assembly. And this is so that we can like visualize what exactly needs to happen with this stuff, right? Like we have these little M stores here and there, more M stores, right? And then each of these has this like call and wrap thing, right? Which this is a pretty common pattern as well. Just making a call, if it throws, just bubble up that revert data, right? And so, yeah, this is like our high level implementation here. And once we have this, now we have something very clean and understandable to work from for the Huff implementation. And so that's going to be here. So up top, we have our imports. We got, ABI related things. I think we also have, do we have libabi? We don't. But yeah, we do have, again, the constructor. So this is what happens in the very beginning. This is doing the ownership set. And then in the main macro, right, the entry point to this whole thing. Structure is pretty familiar internally, but something that's really important here is we have these directives, right? We have, what does it do? We do selector ordering, which is kind of a gas optimization, just, whatever you expect to use the most, just put it at the top, things like that. But this is the big one here, right? The panic cases. These are like your exceptional reverts. Now in this case, it's just whenever a dispatched function panics, right? But if we go under any one of these, if we go to like execute arb, for example, right? We go in here, we have our directives, but here we have panic cases. So we say like, if this panics, if that panics, if we didn't make a profit, right? And then any of these items in here, we can actually go and look for those, right? So if we look at fulfill basic order, I believe that might actually be imported. One sec. Lib call. Yeah, there we go. So this is the call, like fulfill basic order, right? This is one of the external calls we make. And then we can see that the actual like panic case happens in here, right? So we know exactly like where things panic and where it bubbles up from. And so that makes it a lot easier to debug whenever we're, doing these kinds of things. But yeah, so we have our different functions. They pretty much all do similar things here, right? We jump to the thing. We've got, error checks, things like that. We have, these last little things that happen if you are actually the owner, obviously restricting as much as possible, et cetera, et cetera. Won't go too much into implementation details, but that's the basic idea is you want to make sure it's very readable, very understandable for anybody that needs to review it, anybody that wants to audit it. And even in this case, this actually isn't even the most optimized way you can do this. Like there's plenty of opportunities for more. But the idea was like we wanted to get some Huff into production and show people like what that actually looks like, right, in terms of readability and things like that. So I'm gonna go and cut the stream from there. If you guys have any questions or anything like that, let me know. I'm also gonna grab those. Let me grab that optimization rule thing real quick. Right. Okay. So in the EVM, or sorry, in Solidity, we do have. One second. Simplification rule. We do have two different kinds of optimizers, right? So we have the like bytecode optimizer or peephole optimizer. And so this has to do with like the actual generated bytecode. We can actually kind of clean up a couple of things from the SolC output. That like optimizes like the actual bytecode itself, and then we also have the Yule optimizer, which does like higher level optimizations with a bit more context. I think that's probably going to be a bit more useful. Um, for people that are writing Huff, because generally you have a lot of context on like what you expect things to look like, how you expect them to behave, even though you're writing a low level contract. So give me 1 second. I think I might have found it. Rule list is what we're looking for. Okay, so let me get you on the main branch. Okay, so here's the Yule optimizer in general. Of course, it's got like a lot of stuff there that isn't like super useful, but we do have things like simplification rules built in here and there. And then I think there's one more under EV ASM. 1 sec. Oh yeah, here it is. Perfect. Okay, gotcha. So this one here, this last link, if you hop into this, you can actually see these little rules, right? Of like push pop, right? Op pop, op stop. So like if you push things to the stack and then you immediately stop, you don't have to push them. Things like that. Double swapping, double pushing, just stuff like that, right? Like just very simple rules as to like how you can actually like optimize, the kind of code that you're writing. Now, in terms of right, so stack swap and pop operations. So, like I said, this one goes a little bit deeper. Let me pull up the article for you real quick. All right, so this is what you're looking for in terms of stack schedule optimization. And so, yeah, like I said, it's a pretty long paper. You don't have to read through the whole thing. Just get a rough idea of like what it's trying to do, and you'll kind of see like kind of the idea, right? Is like you want to push as many items to the stack as possible up front. So let's say, for example, you want to, yeah, but keep the same functionality exactly. So let's say, for example, you want to, I don't know, push something, like put something in memory and then return it, right? So maybe something that you might see is something like this. Just 1 second. So this is a pretty common one, right? You just put something in memory, return it, right? But another way that you can do this is something like this, right? And so this doesn't seem like an optimization, right? Like it's the same number of opcodes, right? But like what this allows you to do is in certain cases, right, it might just be profitable to do like dupes instead of like repushes, right? And things like that. Or maybe you can like reuse the output of another opcode, while you're scheduling the next opcode, right? So like obviously nowadays we have push zero, so it actually is just profitable to just push a zero. But let's say for example, like these things are still doing like push 1 0 0, right? Like something we can do instead, right, is something like this, and we just saved a little bit of gas by doing that duplication, right? So again, these are like really simple, like rudimentary like examples, but like this can actually be composed like using like more complicated opcodes, more complicated control flow. You do get a lot more benefit out of it. How do you deal with like 5 unnecessary swaps and dupes, right? So this also has to do with this sort of like stack scheduling system, right? Where like you want to, it's almost easier to write it like Yule code, like that kind of Yule code that doesn't use unnecessary variables, right? Where you just kind of have this Lisp-like syntax of like you just have like functions and functions and functions, and so by using those as like dependencies, again, this is kind of hard to explain from a high level, but basically like what that is you're creating a sort of graph of opcodes that depend on other opcodes to get values from them, right? And that's what the tree-based IR paper goes into, right? Is that like these things are like these opcodes are essentially nodes in a graph, right? And so like the dependencies, like what they depend on are the edges in that graph. And so if you traverse this graph depth first, then you find that like you're pushing all the items to the stack that you can up front. And by having all of that, it reduces the amount of swaps that you need. And in cases where you would just be pushing otherwise, you can actually take advantage of dupes, right? And things like that. So there's really cool stuff that you can do with that. Obviously, it's a little bit limited in the EVM still because even though the stack depth is like over 1,000, like we still can only interact with about 16 items at a time, so there are limits to this kind of system. But generally for Huff contracts, I've never seen the stack get so deep that you can't interact with something like that. So yeah, so automatically that's something that you would essentially just have to build a tool for, right? Something that can take this sort of system and generate this. Now actually a little, I guess a little bit of I don't know if this is public info yet, but so Viper is getting a rewrite to their IR, and so the Viper IR is actually going to behave very similar to this, right? So um, it's basically going to look like a Lisp the way that it's like written, but because of that, those opcodes are structured as a graph, and you'll actually be able to get this like crazy good stack schedule. So I think it'll absolutely be worth checking out the Viper IR, like tinkering with that a little bit, and then seeing what the bytecode looks like that the IR outputs, and then you can kind of start building like your own like it's almost like your own like internal like optimization rules, right? That you have in your head, and looking into compilers is a really good way to learn more about that, right? Because compilers are just automating that process of like creating these optimizations. But with that, I'm going to go ahead and wrap this up. Thank you guys so much for being here. Appreciate you coming and checking out this speech. And yeah, have a good day, guys.